Hello everyone. In this lecture I am going to discuss about fundamental of different types of welding heat source, especially used in different types of numerical method. Till now I have already discussed in details about point and line heat source. In this lecture I will discuss about different types of you can say distributed types of heat source like Goldach double ellipsoidal heat source. Then I will discuss Gaussian distribution of arc. I will discuss also some Avogadro shape heat source model. Apart from this thing, I also will discuss some semi ellipsoidal types of heat source model in details. In this lecture, I will discuss in details how this heat source generally developed and how its derivation is done. Everything in step by steps I will discuss in this lecture. And I will also show you where is the main application of these types of heat source. Mainly these types of heat source we used in different types of numerical model. All of you are very well familiar about numerical modeling techniques like finite element method, then finite difference method, then finite volume method, boundary element method. These are the very common numerical method which is a approximate method which have nowadays very wide application in the field of heat transfer, then structural analysis, vibration, fatigue and different types of engineering field. It has lot of application. So, I will show you how this different types of heat source used in these different types of numerical method, especially in finite element method, how we can use this distributed heat source and how we can use this distributed heat source as well as how we can predict the thermal history for a welded structure more accurately you can say, and which is very well comparable with experimental results. So, this is the content of today's lecture. Here I will discuss about first details about Goldach double ellipsoidal heat source model. Then I will discuss about semi ellipsoidal heat source model. Then Gaussian distribution heat source model also I will discuss. Apart from these things, I will also discuss about Avogadro shape heat source model. So, first of all I will discuss about Goldach double ellipsoidal heat source model. All of you are very well familiar about point and what it is called line heat source model. Till now I have discussed in details in this course at the beginning itself. Now I am going to discuss about this Goldach double ellipsoidal heat source model. What is these things? It is actually moving volumetric you can say heat source, which generally can be considered for modeling of welding arc you can say, based on the double ellipsoidal distribution which is proposed by Goldach et al. In 1984. You say, though it is developed long back, nowadays also it has so wide application in the field of welding you can imagine, because this is a very popular heat source model which can give you a result which is very well comparable with experimental results. Now, this double ellipsoidal it is a equivalent heat source model you can say, which is proposed by Goldach, which is defined by 6 parameter. As I have written this 6 parameter, how these 6 parameters come, everything in details I will discuss, which generally describe the input energy which is confined to double quarter ellipsoid. Here one thing you should keep, this double ellipsoidal model is generally described in a double quarter ellipsoids. This you should keep, how it is that also I will discuss, and it is generally valid for normal condition of welding. This you should keep it in mind. And this heat source generally is a non-axisymmetric heat source. This you should also keep it in mind. Why non-axisymmetric, that is also I will discuss. Double ellipsoidal heat source model, how it is, that I am little bit going to discuss here. I have already shown you the geometry of this double ellipsoidal heat source model. Like let us consider this is a weld specimen where generally heat source start from from here, and when it will move, you will observe that the heat source shape is become due to movement, it is become like this. This you can say, this is become like this along weld line. Okay. Now, this you can divide into two part, like you can see this front part is resemble like a one types of ellipsoid, and this back part is generally represent another types of ellipse, this you can say. So, this is one part of ellipse and this is another part of ellipse. That is why let us consider this front part ellipse have a what it is called axis, you can say, which is, let us consider I am representing as front as well as I am representing CF, and back part of this ellipse axis I am just representing as CR, as it is a rear part, that is why I am representing these things like this. Now, apart from this thing, along the thickness direction, if generally what happens, so if I just draw this ellipse like this, two ellipse like this. So, this is one front part ellipse and this is back part ellipse, and along the thickness direction also you will see there is another ellipse is there. Okay, this is another ellipse is there. Let us consider the thickness of this ellipse is through the thickness of the penetration, that I am showing here. Here you can see from here to here, from here to here, this is I am representing as a distance through the thickness, how much penetration from here to here is there, this is I am representing as V. And apart from these things, you can see, let us consider, I am just considering this thing, let us consider this is your x axis, perpendicular direction is y axis, and let us consider this is our z axis. Here I am considering like this, and this is the welding direction. So, welding velocity I am representing as V, this you should keep it in mind. So, I am writing welding velocity or traverse speed, you can say. Okay. Now, it is moving in z direction, it is moving in z direction. Due to this moving, your weld bit geometry can be represented like this. So, you can say this front part of this ellipse is represent with the thickness, it represent a quarter of one ellipsoid, and this back part of this ellipse with the thickness direction, it represent another quarter of the ellipsoid. So, that is why I have written here, it is generally here generally heat input energy is confined to double quarter ellipsoid. Double quarter ellipsoid, why it is double quarter ellipsoid? Because it is generally this ellipse is a quarter of ellipsoid, you see this is a quarter of ellipsoid, you can say, because if it is a full ellipsoid, then top side will be there, right side part also will be there, right side top bottom also will be there. So, you can say 1/4 of the ellipse generally is considered, ellipsoid is generally considering here, that is why it is called a quarter of one ellipsoid. So, here we are considering 2/4 of the ellipsoid, where generally we are considering the heat input is confined. It is looks like this heat source model is looks like this only. So, here what is our A, B, then what is CF, CR, that idea you got from this diagram also. Like here you see this is our CF, this is back portion of the ellipsoid is CR, you can see this is CR. Then what is A is the ellipse minor axis distance, that is generally represent along x axis is A. Similarly, through thickness, that is y axis direction, it is represented as B. What I am telling, understand. So, what are the parameters here we are getting? We are getting what it is called 4 parameter from this double ellipsoid geometry. What is those parameter? Those parameter is A, B, CR, Cf. This is 4 parameter. Apart from these 4 parameters, another 2 parameters also are there, that is generally called Fr and another one is called Ff. This what is Fr and Ff, that I will discuss in next slide. So, what is Fr and Ff? You can see Fr means heat fraction. What is the portion of heat is generally in front ellipsoid, and what is the fraction of heat in what is called rear ellipsoid. Generally that things is generally Fr represent rear ellipsoid, how much heat is there, it is a fraction, dimensionless quantity, and what is the Ff is generally what is the heat is generally fraction is in front portion of the ellipsoid. Okay, this you should keep it in mind. So, based on these things, this double ellipsoidal what it is called heat source has two part, you can say. One is generally represented for front portion of the ellipsoid, another one is represented as back portion of the ellipsoid. How it is coming, everything in details I will discuss. And what is this Fr and Ff? Generally Fr is represented as 2 into Cr divided by Cr plus Cf, and Ff generally represented as 2 into Cf divided by Cr plus Cf. This you should keep it in mind, because if we consider this fraction, considering this what it is called Cr and Cf, if we calculate the Fr and Ff like this, then what happens, it give us more accurate result. Different researchers generally use different types of fraction of this thing, but what happens by optimizing those different fraction of Fr and Ff, it is observed that if we consider this fraction, this gives us very accurate result, which is very close to what is called experimental result. This you should keep it in mind. So, what are the 6 different parameters? You got the idea. So, these 6 different parameters generally is A, B, Cf, Cr and Fr, Ff. Now, in this you can say in this equation there are another 3 parameters are there, that is generally our input parameters, you can say during welding. You can say one is called V, which is welding speed, or you can say welding traverse speed, then T is the welding time and tau is lag factor. What is this, all in details I will discuss in this lecture. So, these 2 equation always you should keep it in mind. Here this QF have a unit which is generally you can say watt per, you can say meter cube, that means this is a volumetric heat distribution. This is a 3-dimensional heat source model. Okay. So, it has also a unit of watt per meter cube. This equation is used for front portion, generally this heat input we used in front portion of the double ellipsoid, and this equation is used for, this heat input is used for back portion of this, you can say back portion of this double ellipsoid. How it is, that I am just showing, this is the back portion of this ellipsoid. Okay. This is also a quarter of ellipsoid, this you can see. Now I am going to discuss about how this equation generally came. Step by steps I will discuss now in details. Okay. For derivation of this double ellipsoidal heat source model, let us consider Gaussian distribution. So, here the Gaussian distribution you can write Gaussian distribution of the power density in an ellipsoid. Let us consider this ellipsoid with center 0 0 0. What is the ellipsoid center? This is the ellipsoid center. Let us consider this O represent the ellipsoid center. and let us consider its semi axis is A, B and C, which is parallel to, which are parallel to the coordinate axis you can say moving coordinate axis, that you can say is x, y, and here in z coordinate I am writing as zeta, which is the moving coordinate. I am writing this x, y, zeta. Okay. The Gaussian distribution can be written as, you know these things, written as like here q, x, y, zeta, and you can consider here t also. T is also a parameter here, which is equal to your q max into, you can say, e to the power minus a x square into e to the power minus b y square into e to the power minus, you can say, c zeta square. So, here generally in this case we will consider two coordinate system. One is called moving coordinate system, that I will represent it as x, y and zeta, and another one is called fixed coordinate system. Fixed also, this is called local coordinate system. This I am representing as x, y and z. This you should keep it in mind. These two different coordinate system I will use. So, let us consider this is a weld specimen where welding is carried out. Okay. Now, so fixed coordinate system you can represent it as, let this is your x, this is your z, and through thickness this is your, you can say through thickness this is your y. Okay. And another coordinate system I am representing as, which is moving coordinate system. I have already told you in details what is moving coordinate system. This moving coordinate system, which has a axis system x, then its thickness direction is y, but its z axis is, this z axis generally is represented as, this z axis of this moving coordinate system is represented at zeta. This you should keep it in mind. Okay. So, the moving coordinate system means the heat source coordinate system. This heat source is moving with a welding velocity. This is, you can say, welding speed v, what I am telling, understand. So, and it is varying with time. This you should keep it in mind. So, in this moving coordinate system, how the power density distribution in Gaussian distribution way, that you can represent it like this. What is Gaussian distribution? You are very well familiar about these things. So, I am not going in detail to discuss again these things, little bit I am just telling you. Gaussian distribution means it is a, you can say, a normal distribution. It is a probability distribution that is generally symmetric about mean, which showing that data near the mean are more frequent. These data near the mean are more frequent in occurrence than data far from the mean. This you should keep it in. How it is, that also I will show. It generally appears as a bell curve when we graph it. So, what happens, this you should keep it in mind. So, it is a normal distribution, and it is also generally considered as a probability density distribution types. How it look like, these things also you know very well. So, I am not going in details about this thing, little bit I am just showing how the Gaussian distribution is looks like. Generally Gaussian distribution is looks like this. Okay. So, this is generally, you can say, 1 sigma plus sigma minus sigma, and this middle curve generally represent your mean. Here I am writing mean, and this have a percentage which is around 68%. Then after that 2 sigma, this is 2 sigma, this 2 sigma generally have a percentage which is you can say 95 point generally 5, somewhere it is written, somewhere it is 95 itself, and this 3 sigma generally is considered as, this is minus 2 sigma, this is minus 3 sigma, this is plus 3 sigma, and it is, its shape is also bell shape. So, this is here this percentage of 3 sigma, you can say this percentage of 3 sigma is 99.7%. This you should keep it in mind. This is generally called Gaussian distribution. What is y axis? Y axis represent probability density. This is actually your probability density. This you should keep it in mind. So, what is Gaussian distribution? You got the idea, because this is also you know, you should know. So, this Gaussian distribution of a double ellipsoid generally can be represented in a moving coordinate system, can be represented like this. From this equation, what is the unit of this? Its unit is always, you should keep it in mind, watt per meter cube, because this is the power density distribution. Power density means power per unit volume. This you should keep it in mind. Okay. Now, from this equation generally how this double ellipsoidal moving heat source equation is coming, everything in details I will discuss. Here generally this moving coordinate zeta, which is equal to, you should keep this thing in mind, z plus welding velocity into tau minus t. What is tau? Tau is called lag factor. What is lag factor? Lag factor generally represent generally the initial position of heat source. Let us consider this O represented our fixed coordinate origin O, and let us consider this O dot represented, O dot is represented as moving coordinate center. Now, let us consider our heat source started, initial position of heat source is, let us consider this is the initial position of heat source, okay, which is behind the, you can say which is behind the fixed coordinate heat source. So, this so let us consider this is your initial position of heat source, Now, let us consider the welding velocity is V. So, I have already told you welding velocity is V. So, generally what is lag factor? Lag factor means the time required from initial position to, you can say, fixed coordinate position, how much time it is required with a welding velocity of V is known as what it is called, lag factor. So, lag factor is a time, you can say lag factor is a time, it represents the initial position of the welding heat source. Now, so from here to here, fixed here to here, how much time it is required, tau, this is generally represented as what it is called, lag factor. This you should keep it in mind, that means time required from initial position of heat source to fixed coordinate position, how much time this heat source is required with a velocity v, that is generally called as lag factor. Let us consider for a particular time t, let us consider our heat source move from here to here. This is generally its take a time t. So, you see what is time t? T is the time required for moving of heat source, this you can say. because this relationship I am just going to show how it is coming. Okay. Now, let us consider, I am considering a point, I am considering a point in moving coordinate heat source, I am considering a point. Okay. So, I am taking different color, that will be better. So, I am considering a point P, this P have a distance from moving coordinate system is, let us consider zeta, and from fixed coordinate O2, this P point distance is, let us consider your Z. Okay. So, what is Z? So, here I am writing Z is equal to, you can write as Z is equal to your OP, then here O dot P means from central distance of moving coordinate system to P, point P is zeta. Okay. And initial position, let us consider initial position of the coordinate system is, let us, here I am considering as you can say I. So, here I am writing I O, it is representing, you can say it is representing the lag factor T into velocity of the, you can say welding heat source. So, IO. So, now I am going to make a relationship. So, for a time T, generally how much distance this heat source move? So, for a time T, the heat source move, total time T, the heat source move from. So, for here I am writing for time T, the total distance travel by heat source, this you can write as I into, you can say I into what it is called O dot. So, I into O dot is what you can say V into T, correct. So, I O dot you can write as, so I P, here I am writing I P, you can write as I O dashed plus you can say O dashed P. This you can write as I O dashed, already I have written as V T, and O dashed P is what? O dashed P is generally considered as zeta. Zeta means with respect to moving coordinate system, what is that distance? P point distance, correct. So, what is IP? So, IP you can write as like what? IP you can write as IO plus you can say IO plus OP. So, this is equal to, you can say VT plus zeta. So, what is IO? IO is already that is distance between initial position and fixed coordinate system. I have already told you this is actually V into tau, lag factor. And what is OP? OP is actually, you can say OP is Z, that means from fixed coordinate to point P distance is equal to, you can say Vt plus tau. So, what is this zeta is coming? So, zeta you can write as Z plus V into tau minus Vt. So, this you can write as Z plus V into tau minus T. So, this is a very important relationship between what? Moving coordinate system and what it is called? A stationary coordinate system. This you should keep it in mind. Now, from here one thing you should keep it in mind, if the initial position of the heat source is same as O, that means fixed coordinate system, then tau will be 0. That means, if tau will be 0, then this moving coordinate system you can, that means if tau is equal to 0, when tau will be 0? If I and O are same, correct. So, if I and O are same, then you can say your moving coordinate system zeta equal to, you can write as what, z minus v into t. This you should keep it in mind, okay, if the same, if it is same. And another things, if the heat source instead of starting beyond the fixed coordinate, if it is a start from front portion in front of this fixed coordinate system, generally here some instead of plus, there will come z minus v into tau minus t. These types of relationship generally will come. Okay. So, that I am not further deriving, because you will be able to derive these things. Okay. Now, I am going to discuss how this what it is called relationship between fixed coordinate system with moving coordinate system is coming. Here we generally consider the welding is moving along the z direction. That is why here I have written zeta is the moving coordinate, which is moving, which is varying with time, is a function of z, which is z is the stationary coordinate system, plus v into tau minus t. This you should keep it in mind. Let us consider this is, this I am representing equation number 2, and this Gaussian distribution of arc I am representing in equation number 1. Now, generally from this equation, how the double ellipsoidal heat source model is coming. Now, these things I am going to discuss in details. Now, generally this Q max is the maximum value of the power density at the center of the ellipsoid, because which I have already represented in last slide itself. I have shown Q x y zeta into t moving coordinate heat source. This you can represent it as Q max into e to the power minus a x square into e to the power minus b y square into e to the power minus c zeta square. This is the equation for moving coordinate system. This you should keep it in mind. Now, what is Q max? Q max is the maximum power density, you can say maximum power density. Its unit is, always you should keep it in mind, watt per meter cube at the center of the double ellipsoid, at the center I am right, at the center of the double ellipsoid. Now, how we can find out this Q max value? For finding out this Q max value, here we will use conservation of energy. So, by conservation of energy, what we can write? By conservation of energy, generally this heat in this double ellipsoid, whatever the double ellipsoid I am just showing, this heat is of this double ellipsoid is coming from welding power source, correct. So, welding power source, let us consider this welding power source providing a welding current for generating this arc is equal to I, welding voltage is equal to V, and let us consider power source efficiency. Always you should hit, this is the power source efficiency, which is, let us consider eta. Okay. So, the energy supplying by the power source, you can say, so power supply by the power source, you can write as Q, which you can write as eta into voltage into current, its unit is watt, this you know. Okay. Now, this much power is supplying from the arc, and this is generally distributing where? In this double ellipsoid, this you should keep it in mind. So, here what are the things we will use? Now, here whatever the power supply is giving, this is distributing in the double ellipsoid. That is why here we will use conservation of energy. So, conservation of energy tell eta V I, okay. This you can represent as Q, which is supplying, this is distributing over the double ellipsoid, this you should keep it in mind. So, this distribution how we can write, here you can see this double ellipsoid, here this is varying, how it is varying. So, here you see little bit, this you should keep it in mind. So, this is your x axis, this is your z axis, and through thickness it is your y axis, this we have considered, correct. So, you can see in this double ellipsoid, this along x axis left side right side generally the arc is spreading. Let us we are considering this arc is spreading, initially we are considering let us for infinite distance. After that generally we will use some boundary condition, we will impose some condition, based on this generally we will limit our value of this a b, this we will find out, okay. This a b value distribution we will generally limit, that I will show you. So, here one things you can observe that here generally this q you can represent along x axis, it is let us consider minus infinity to infinity. What is minus infinity? This is your plus x axis and this is your minus x axis. That side let this is our center 0 0 0. So, left side right side I am considering plus infinity to minus infinity. Then y, here one things in this y generally whatever the arc is coming, you see this double ellipsoidal, one things you can observe that half the only lower portion through thickness portion or half portion of this ellipsoid is there along y direction, top portion of the ellipsoid volume is not there, this you can see. That is why here you can say from surface which you can consider as 0 to let us infinity, bottom side infinity y direction, what I am telling understand, 0 to infinity, okay. And along z axis you can say along z axis this ellipsoid is varying from minus infinity to plus infinity. But one thing you should keep it in mind, in this ellipsoid how this ellipsoid is look like, this ellipsoid looks like you can see like this, only bottom side ellipsoid is there, top side is not there. That is why as this bottom side of part is only there, that is why for y case I have started from 0 to plus infinity, this you should keep it in mind, okay, because top part of this ellipsoid is not there, only bottom part of this ellipsoid is there, clear. Whereas you can see this along z axis left side right side part is there, along x axis you can say left side right side part is there, left side right side part, that is why it is started from minus infinity to plus infinity, these things you should keep it in mind. This you can write as how, so q max into e to the power minus a x square e to the power minus b y square e to the power minus c z square, c z means zeta square dx dy dz, okay. So, this is by conservation of energy, this you can write like this, clear. So, how the equation is coming, this idea you got, okay. Now, by little bit calculation what you can write, this minus infinity to plus infinity you can write as 2 into integration of 0 to infinity, okay. This you can write as, and q max you can is a constant value, I am taking it out, 2 into e to the power minus a x square dx, correct, this we can write. Similarly, we can write integration of for y part 0 to infinity e to the power minus b into y square dy, okay. And for z part we can write 2 into integration of 0 to infinity, because this is minus infinity to plus infinity. The law of integration, you know these things, okay, I am not going in details, minus e to the power minus c into zeta square, you can say d zeta, this is the zeta, this you should keep it in mind, because here we are considering everything in moving coordinate system, that is why this should be also zeta, not zeta. Okay. Finally, what are the things we are getting? 4 q max, because this 2 is there, another 2 is there, integration of 0 to infinity e to the power minus a x square dx, integration of 0 to infinity e to the power minus b y square dy, and integration of 0 to infinity capital C zeta square d zeta. These things you got, correct. I think this is now very clear to you. Here one thing you should keep it in mind, why x and y we are considering as similar to fixed coordinate system, because whatever the x coordinate in fixed coordinate system, in moving coordinate system also it is same, because both are parallel to each other. What I am telling is x and y, these are two parallel component of fixed and moving coordinate system, that is why these are same for both the coordinate system, which I have already discussed in my previous lecture itself.